Hello, and welcome to Cognitum, a show dedicated to exploring the present and future of science and technology. I'm your host, Iosif Gershteyn. Joining us tonight is Dr. Crane, a professor of statistics at Rutgers, author of Probabilistic Foundations of Statistical Network Analysis, and co-founder of Researchers.ONE. Harry, welcome.
Thanks for having me.
So tell me, how did you get interested in the topic of probability?
Well, as you mentioned, I'm a statistician, and the way that I got interested in statistics was through my interest in probability, which is really something that I've been involved in and been interested in ever since I was a young kid. So when I was a kid, and really my interest developed in much the same way that a lot of the classical probabilists in the 1600s, 1700s, who were first developing the theory of probability were for the purpose of better understanding games of chance, randomness, and as applied to gambling. And so when I was a kid, I remember that there was a guy in the neighborhood named Reds Gabriel who he worked out of the local Dunkin' Donuts. So he worked in the Dunkin' Donuts around the corner from my house. And what he would do is he would sit there all day, and people would come, talk to him, meet with him. They would leave. Otherwise, I would see him walking around the neighborhood. He didn't have a job, but he seemed to be doing pretty well for himself, money-wise. Of course, later on, I learned that he was a bookie. And what he was doing in Dunkin' Donuts was people were coming in betting on football, horse racing, lottery. And what really struck me was that he wasn't educated. He probably had a 6th grade education. And he also didn't even pick sides on these bets. He was allowing the people who came in to bet on whatever side they wanted. But at the end of the day, he was walking away with the money. And so I thought, well, there must be something going on there that I'm not seeing, because I was always under the impression that you can't win by gambling or just by gambling on random events. And so what exactly was it? And so that kind of got my interest in probability, both intellectually but also practically. I actually, as a kid in school in 6th grade, I tried to implement Reds' strategy. I was running my own bookmaking operation in the 6th grade class. That didn't last very long once the principal found out. But I maintained this interest throughout college and until now. And now my interests, of course, have developed in various different directions, but I'm still very much interested in understanding anything related to probability, the concepts of reasoning under uncertainty, dealing with risk, and how we bring these ideas from theory into practice.
Well, risk dominates our lives. Most decisions, most consequential decisions we make are under uncertainty. So more and more people look towards statistical knowledge to make their decisions. And what I'd like to know more about is where do you think the knowledge that we can get from statistics and probability comes from, and perhaps what are the problems of our common understanding of them?
Well, I think that there's many different ways to think about probability, and if someone were to ask, what is the definition of probability or what is probability, there's really no one answer. It's something it's a concept that appears in a lot of different settings, and it might have a slightly different meaning or a very different meaning depending on the context. So just to give you an example, maybe the most familiar or the most common way to present probability as it's taught in introductory statistics courses is what's called the frequentist or the frequency interpretation of probability. So you take the example of having a coin and tossing a coin a large number of times. If I were to toss the coin 1,000 times, how often will it come up heads? If I tossed it 10,000 times, how often will it come up heads? And intuitively, we'd expect that it would come up heads about half the time. And that frequency of the time that a certain outcome occurs is interpreted, that's what's taken to be the probability according to the frequency interpretation. And so that's one way of thinking about probability, which has some you can think of it as having some objective content, right? The probability in this case has nothing to do with what I think is happening. It actually is determined by the properties of the process that we're repeating, this coin tossing process. Another way to think about probability is what's called the Bayesian, or the subjective view, where so in the previous example, I had to toss the coin a large number of times in order to get at this frequency or this probability. But there's many things that we can't repeat, but we can still express a probability about them. And this is where the subjective view comes into play, where when I might state the probability of an outcome, so for example, I might say that the chance of the Patriots winning their next game is 80%. What I'm actually saying is that is my degree of belief. That is my level of confidence in some sense in the chance that that happens. And so that's a more subjective point of view. And the way that gets kind of brought to bear in real life, or understood in terms of real life outcomes, would be that when I say the probability is 80%, what I actually mean is I'm expressing my willingness to bet on the outcome, or willingness to offer a bet to you at 4-to-1 odds on the opponent, because 80% over 20% would be 4-to-1. So those are the two predominant textbook definitions of probability. There are, of course, other ways in which probability comes up in everyday conversation. You use the word probably, possibly, plausible, all kinds of language that we're familiar with and that we can kind of reason with intuitively. But those aren't necessarily taught in the textbook. But one of the things that I think is really important to understand is that these textbook definitions, whether it's the frequencist or the Bayesian interpretation, they're worked out mathematically, and there's sound theory and rigorous kind of mathematics behind it. But there is a difference between the textbook and when these ideas get kind of brought to bear and applied to real-world problems. And that's something that I've become very interested in. And the thing that and so an example of that, which is happening right now, which is a very significant, great significance not only to science but also to society in general, given our reliance on development in science, is something called the replication crisis.
The replication crisis, as far as I understand it, is about a project that tried to test the replicability of a number of studies, I believe in psychology, that about half of them failed to replicate during this project.
Yeah, more than half. Yeah, actually. But yeah, so what's happening is that when I was in third grade, I learned the scientific method, and the last step in the scientific method, as I remember it, was to repeat the experiment, right? And so what's happening in the literature is that scientists, whether individual scientists are repeating their experiments or not, I don't know, but they publish their results in the literature, and then other scientists in other labs try to repeat that experiment. And so they repeat the same procedures, and they draw conclusions using the same methods, and they see whether or not they got the same conclusions as the original group. If they do get the same conclusion or arrive at the same conclusion, then they would say to have replicated that original result. If they fail to do that, then the result did not replicate. And what we're finding through studies like the one you just mentioned is that they're actually going in and systematically trying to replicate many studies that have been published in the top level journals in the respective fields. What they're finding is that in some cases, there was one, the biggest study had about 100. They tried to replicate they repeated the procedures of about 100 psychology experiments, and they were only able to replicate 39% of them. So
less than half.
In more than half of the cases, the published result didn't stand up to additional scrutiny. More recently, there was a replication project with a smaller sample size of just papers that were published in Science and Nature. These are the two most prestigious journals, and 61 or 62% replicated in that case. So this is empirical evidence that perhaps the published literature isn't, this is empirical evidence that the published literature isn't as reliable as we expect it to be, or perhaps we think that it is. And and how this relates to a statistical problem is the way in which these conclusions are drawn in many fields is through is within a statistical framework called hypothesis testing. And so, without getting into the details of this, essentially the way that hypothesis testing works is that you, a scientist, have a hypothesis, or you have some proposed model of how the system that you're studying works. And so you make some assumptions about the model, about the real world. And then you collect data, you run experiments, collecting data under the assumption or under the presumption that the data is coming from your assumed model. Okay. Once you collect the data, you now want to compare to what extent the data is consistent with your initial hypothesis. And so this is done, one way to do this, and the predominant way this is done is through what's called a p-value. So the p-value, you can think of it as, well, you would compute, what is the probability that I would have observed the data if my hypothesis were true. That's essentially what a p-value is. A p-value is not the probability that the hypothesis is true. P-value is better to be understood as a measurement of the extent to which the data, the real world, something you observed, is compatible with your assumptions. And so the way it gets used is that if this p-value is small, that indicates that the data you observed is very inconsistent with your initial assumptions, and that's what leads to what's called a statistically significant finding. So if the p-value is small enough, and in many fields the default cutoff value is 5%, if the p-value is less than 5%, then you can reject, or you're warranted in these fields to reject your initial hypothesis and to draw what's considered to be a conclusive finding on the basis of that calculation.
So when you say that it's the p-value is below 5%, what it means is that there's 95% chance or higher that the results that have come in are in line with the assumptions.
So it's important not to confuse the definition of what this p-value actually means. So, and this is where it becomes interesting to actually see how this replication crisis could come about, even in the absence of any of these additional concerns of fraud, misconduct, or just misapplication of statistics. So there certainly are concerns about that maybe the scientists who are applying these methods don't understand them very well. Or maybe they have incentives to be dishonest in order to get their papers published, and all of that is true. But in order to appreciate the statistical side of this, it's possible that we would have this replication crisis, and in fact probable that we would have some kind of replication crisis, even if none of that existed, even if every individual researcher were to apply this theory absolutely correctly at the individual level. And so there's a difference between, and I'll give you an example in a second, the difference between individuals applying a theory of statistics or a statistical method and how the results of those individual methods get reported at the aggregate level. Okay, so what the p-value indicates at the 5% level, this is what's called in statistics a type 1 error rate, which is under the assumption that if the hypothesis actually is true, if the initial model is correct, a type 1 error would be rejecting the hypothesis when you shouldn't reject the hypothesis. And to reject or to set this p-value threshold at 5% is to control this error rate at the 5% level. So you should only make this error about 5% of the time. Now, that doesn't sound very high, or maybe that sounds too high at the individual level, but to see how it affects things at the next level, the systems level of the academic publishing and scientific publishing system, one way to think of this is imagine having, imagine I have just as an illustration, that the experiment I'm going to run is I'm going to pick out of a box with a box of balls. I have balls numbered 1 through 1,000. And my hypothesis is that I'm going to draw one ball out of this box, and my hypothesis is that all of the balls are equally likely to have been chosen. Okay. But the way that I'm going to compute my p-value is that I'm going to just look at the number on the ball, and if it's a 1, then I'm going to compute just the probability of having observed a 1 given, well, I'm going to indicate whether I observed a 1 or didn't observe a 1. Okay. So the probability of observing a 1 under my hypothesis is 1 in 1,000, right? And the probability of not observing it is 99.9%, right? Now, if I run this experiment, and I happen to pick a 1, I'm going to compute my p-value of having observed that given my assumption, and the p-value would be 1 in 1,000. So that would be a statistically significant finding, and of course it would be a false positive in this case. But the probability of that happening for me is 1 in 1,000, so that's where it's controlling the error rate. Now imagine having 1,000 scientists all running this same experiment. What's going to happen? Well, one of them, on average, right, one of them is going to pull this ball out. For that one, they are controlling their error rate at this level. The p-value means that they've only made an error 1 in 1,000 times for this individual. Okay, but they're going to report it as if it's a statistically significant finding. The other 999 get a p-value of 99.9%. They have nothing to report. So that doesn't get reported in the literature. The one that did pull the value does get reported. The journal now reports this as a p-value of 1 in 1,000. But what's the actual p-value from the journal's perspective? Well, from the journal's perspective, there were 1,000 people, and whoever observed this outcome was going to report it to them, and whoever wasn't going to report it to them. The actual p-value is very close to 1 in that case. But that's not what gets reported. And so that's just an illustration of how all of the math can be correct at an individual level, but then when you go to the aggregate level, when you see how these things actually get reported, that somehow distorts the meaning of the probability from the way that it's presented in the textbook.
So basically, because negative results don't get reported and positive results do, even spurious results done by scientists who are following the method precisely and honestly will still, at the systems level, skew towards spurious results.
Yeah, so this is something called publication bias, and within the framework of what I just described to you, there is it's inevitable that there's going to be errors in the literature because there will be false positives according to this. The only way to avoid false positives under this setting is to never reject. Okay, if you never reject, you'll never have a wrong conclusion. Okay, but you also won't get anywhere, right? So there's a balance between these things, and so what happens in publication bias is that well, as a researcher, so I just showed you a situation in which if everything was on the up and up, we would still have a misrepresentation in the literature. But what actually happens is, as a researcher, I know that the journal is going to evaluate me, not exclusively, but the value of this p-value and whether or not it falls above or below this 5% level is very significant as to whether or not I get my paper published in your journal. And the reason why I care about getting published in the journal doesn't have as much to do with whether or not the results are correct or my methods are sound as it does with a lot of sociological and other incentives that come with that are present in the academic system or in the research system in general, things like tenure, promotion, getting the next grant, and things like that. So if I do an experiment and I get a p-value of 0.06, it's not guaranteed that my paper is going to get rejected, just like if I have a p-value less than 5%, it guarantees that it gets accepted. But what happens is that it definitely increases my chances considerably if the p-value is less than 5%. And so if I get that 6% on the first try, what I'm inclined to do is what's something called p-hacking, which is to collect more data or to maybe assume a different model or do other things to the data until eventually I come up with a 5% or a less than 5% p-value. And in truth, what I should be doing is correcting for all of those extra steps I took, but I don't when I report it into the journal. And so that's what also leads to a lot of spurious reporting. Yeah.
So this is commonly called p-hacking.
So p-hacking, is, as I use it, is kind of a general term of just generally using invalid statistical methods or reporting metrics such as the p-value in such a way that they don't actually mean what in practice, they don't actually mean what they're representing themselves as. They don't mean what they did in the textbook because there was some distortion in the way that the statistical methods were applied. But generally, p-hacking is you have a p-value and you try to kind of chip away at it until eventually you get a number that's less than the threshold for publication. And then that's what you report without reporting all the steps that you took in between. And so there's a lot of talk about, well, what can be done about this? And that's something that I'm certainly very interested in. But in order to I think, make a good effort at trying to resolve this, it's important to understand that distinction between what's going on at the individual scientist level and what's happening at the higher level, at the level of the journals, because these aren't things. All of these factors, including the types of analysis I run and so on and so forth, also any other external pressures that I might be facing, all of that somehow figures into what it looks like or the way that these things manifest themselves once they're published. And so one of the ideas that I've had and that I've suggested is to try to actually get back to the basics of what are these probabilities supposed to mean? The way that they're presented in the textbook, what is it that they're supposed to mean, and how can we make it so that the way that they're reported is as close to their original meaning and their intended meaning as possible. So this is what I call the fundamental principle of probability, which is when we report probabilities, they should mean something. They should have a clear meaning, whatever that meaning might be. And what we're finding, one of the issues with the replication crisis, is that that's not happening. And so the one particular instantiation of this principle would be, so I mentioned earlier the subjective view of probability, where if I give a probability, that's the odds I'd be willing to offer on a bet on the other side of the outcome. Well, if that's what it's supposed to mean, then when I report a scientific finding, and if we care about replication, then perhaps one thing I could do is I could make an assessment I could make a claim as to how likely my results are to replicate. So I might publish something and say, these are 90% likely to replicate. And how do you know that 90% is actually 90%, or that I actually believe that it's 90%? Because under the current model, what I would be inclined to do is to make that as high as possible, because it would appeal to the journal. Well, in order to kind of to address that issue, actually put this principle into practice. Put this meaning of, well, that probabilities are degrees of belief and our willingness to bet at a certain odds into practice, where when I say 90%, that means that I have to put a certain amount of money up. And if anyone doubts that my claims are correct, they can bet the other side, and I would be offering them 9-to-1 odds. That's the best way that I can think of right now to address this issue of inaccurate reporting in the scientific literature. And so the interesting thing is that it actually sounds to some people a bit extreme or a bit radical, but on the other hand, if you think about the effect that science has on a lot of things that we do in society, medicine, technological innovations, and so on and so forth. So scientists have a very big impact on everyday life of people. And it's only right that if they're making these claims that are going to have potentially negative effects, that they also have some kind of that they also face some consequence for that. I'm not saying that any falsely published results should be thrown in jail, or you should lose your job, but
some skin in the game
there should
is
be
necessary.
some kind of there has to be some kind of consequences to at least align the incentives, and to make it more symmetric,
And so, because this problem of replication is serious, and we have more uncertainty about how much faith we can place in the published science that we see. What have you been doing about it?
Well, aside from trying to emphasize this point in the particular case of probability and statistics and how these probabilities don't match up with their intended meaning, it's important to realize also that the replication crisis is just one of many issues with academic publishing. There are the much broader issues of politics and just generally, suppressing ideas that are unpopular. The way that the academic publishing system is set up through this system of peer review is that when an article gets submitted for publication, it's judged at the beginning of its lifetime as whether it's worthy to be published in a particular journal or not. And what's interesting is that contrary to what I think maybe the public would think about this, when an article is rejected from a journal, it's not usually because the results are wrong. It's that they're considered to be of insufficient novelty or insufficient interest, or there's kind of a projection from the journals as to how important this idea is going to be, and that leads, of course, to a lot of. And so this is really feeding a process which is an administrative wing of the academic system. So its primary purpose, and it's really been optimized for this purpose, is to make tenure decisions, grant decisions, and so on and so forth, basically to provide an infrastructure by which it's possible to judge the perceived prestige or perceived quality of work and the prestige of work without actually having to read the work or understand the work yourself. And so what I've done, along with a friend of mine, Ryan Martin, is we've started an initiative and a publishing platform of our own called Researchers.ONE. And what this is an online platform. This is actually a publication platform that's open to anyone in any field, where you can go and publish your work and get it peer reviewed and get all of the benefits, what we call the scholarly benefits of peer review, without having to go through the administrative hoops that oftentimes, actually, when you submit to a journal and you get referee comments, they're oftentimes detrimental to the quality of the work because they don't necessarily serve the purpose of the author. They're serving the purpose of the editorial board and the editor of the journal. And so Researchers.ONE is trying to put the control over this process back into the hands of the authors. And the way that we think of it is, nobody should have more of an interest in making sure that my work is correct, rigorous, accurate than me. But the way that the system is set up now is totally the opposite. We assume that authors don't care so much about the quality of their work, for example, through p-hacking and stuff like that, because they care more about getting that stamp of approval or that indication of prestige. And that's just not what peer review is supposed to be. That's not a scholarly principle, and we're hoping to at least restore those principles and to provide an outlet for those researchers who also believe that this is important, to have an option to publish their work, but nevertheless also get their work peer reviewed and criticized and improved.
That's wonderful. I hope Researchers.ONE continues to grow and succeed.
Well, we've been doing really well so far, and we've only started just 3 months ago, and we've already had a number of papers, over 40 papers published in all different areas: physics, philosophy, math, statistics, and so on. And as more people find out about it, I'm confident that they'll like it and they'll hopefully try it out.
Thank you.
Thank you.
Thank you for joining us tonight with Dr. Harry Crane. We hope you join us again next time as we explore the frontiers of science and technology with the thinkers creating the future.